So this video quickly look at multiple linear regression. So we have a data set for rental bikers, and the response variable is what is the casual count of bikers who are renting bikes on a daily basis, and our independent variables are essentially the environmental factors, which are temperature, humidity, and wind speed respectively. All of these input variables are normalized except the response variable. So a good way to start before using the regression model is to understand whether there is a relationship that may exist between one or more of such variables, and that we'll quickly do using the core function as we did last time. So we have three comparisons between three different variables, so between temperature and humidity, between temperature and wind speed, and then between humidity and wind speed respectively. So you can see that there is a positive correlation between temperature and humidity, while this negative correlation exists between temperature and wind speed. And similarly, we can look at there's one more that we missed. I think it's humidity and wind speed, right? That's negative 0.24. So since some kind of correlation exists between each of these input variables, this may have an impact on the variance that is expected to be explained by a regression model. For that, we need to calculate the variance inflation values, and it's called VIF, and that's calculated by making each of these a response variable and function, and so we will see that these can be explained by the other two variables. So you can see, so there's an LMFIT1 where I've tried to do a regression using temperature as a response variable, and I can quickly do a summary of LMFIT1 to understand what is the R-square value, which is 0.04. And so I can do the variance inflation factor. I can compute that as 1 upon 1 minus this regression statistic value, which is 0.043, and raised to the power 2. I can see that it's fairly close to 1. So it may not have that much of an impact. Similarly, I have to do it for the other two combinations. So I'm making humidity a response variable. I'll quickly do a summary of this. We get the R statistic, and then I will quickly calculate the variance inflation for this, which is 0.07, and this comes to be again close to 1. So again, not much of an inflation effect. Similarly, I'll do it for LMFIT3, which is taking wind speed as a response variable and temperature and humidity as the independent variables. And I can quickly do a summary on this one, get the R statistic, and then I'll quickly do a variance inflation value by plugging in this R statistic value. And I can see that again there's not much of an inflation effect. So once I do the check on whether variance is needlessly influenced or inflated by a pre-existing relationship, once I do that check and I know that that's not going to have such an impact, and then I can proceed with a full-fledged linear regression model. So we'll quickly do that here, and then I can proceed with my residual analysis to understand how good this model is fitting for a given set of response variables and input variables. So I can quickly do a plot of original response variable versus the fitted values. I can see that it's not a straight line, so there's some kind of relationship that is not yet captured, and that's how I have to revise my model. I can also do an R student on this to use the standardized residuals, and then I can see how. First we'll look at one of the outliers, so I'll highlight that in red, and then I can also do a histogram and compare that with normal line. So you can see that it follows the normal line early on till it reaches the first theoretical quadrant, and then it kind of zooms out of the normal line. That means this hints towards a right skewed distribution where most the observations in the positive quantiles. So I mean, more proportion of the proportion of observations which are lying in the positive quadrant are way higher than those elsewhere, and that's why it tends. So mean tends to be higher than the median, and we will see that in the application of skewness as well. So we'll quickly do a skewness, and we can see that the skewness here is positive. That means it's a right skewed distribution. And then we can also do a check on the tail by allowing kurtosis. And kurtosis is 2.45. That means it's a heavy tail distribution, heavy tail towards the right. And that we can quickly check again visually in looking at the histogram. And we can see that there's right tail. And I can proceed with the influencing observations. For example, the observations which are either outliers or they are affecting the response, the Ferret model, whether these observations are going to be present or not. So if I remove one or more of these observations, my model will have a significant impact. And I can do that using something called the hat value. And we can plot these hat values and see how those are distributed for each of the input variables. This is again a scatter plot, and similarly I can do Cook's distance, which is again similar to hat values, but it's a different type of metric which measures the overall impact because of presence or absence of a given set of observations. And then I can see the outline, so I can filter based on a certain criteria. In this case, I'm using a quantile criteria. So I can see that the influential observations are highlighted in red based on their Cook's T distance, and that's a metric. And similarly, hat is another metric which serves a similar purpose. And so I can do a DF fits and DF betas as well.